We live in a world where technology increasingly shapes our lives. As the persuasive technology community well knows, understanding how interactive systems can ethically influence human attitudes and behaviors is key to tackling complex personal and societal challenges, from promoting healthier lifestyles to fostering constructive online discourse. Navigating these challenges or designing effective, persuasive interventions often requires understanding multiple viewpoints, engaging with different arguments, and anticipating outcomes. Yet, accessing and simulating these diverse perspectives realistically remains a significant hurdle. This challenge is central to persuasive technology research. How can we design and evaluate systems that ethically guide users towards their goals? How can we explore the dynamics of influence, argumentation, and consensus building in complex digital interactions? To address this need and empower researchers like you, we developed Apollo, an architecture and open source platform that orchestrates large language models. Apollo is designed as a flexible tool specifically for investigating multi-agent AI interactions. It allows multiple AI agents to engage in configurable, collaborative discourse, providing a unique testbed for studying human-AI interaction, evaluating persuasive strategies, and designing technologies aimed at positive behavior change. Let's see how Apollo facilitates this. The platform greets you with a user-friendly interface. You can define complex scenarios or persuasive goals in the main prompt area and upload relevant documents, perhaps background information for a health intervention, or case details for simulating negotiation, providing crucial context for the AI agents. Apollo's strength lies in its configurability, allowing you to meticulously design your persuasive technology experiments. The system prompt acts as the foundational protocol. Here, you can define the persuasive context, set ethical guidelines, or specify the desired behavioral outcome, shaping the agent's collaborative strategy. Control interaction length using maximum number of turns. This allows you to study the effective interaction duration on persuasion or consensus, while ensuring experiments conclude predictably. Consensus can also end discussions early. Focus on the final persuasive outcome. Toggle Only Show Final Consensus to see the summarized result of the agent's deliberation. Crucially for ethical persuasive technology, the harmfulness detection feature, using the detoxify classifier, automatically flags potentially harmful or coercive language, helping ensure your experiments align with the field's core principles of non-deception and user well-being. Apollo's adaptability is shown through features like Lawyer Mode, an example of how the platform can be repurposed for specific domains. Imagine tailoring this for health coaching, sustainability nudges, or educational support, allowing you to study persuasive dialogue within targeted contexts. Finally, you configure the agents themselves. Select different large language models to represent diverse personas or viewpoints. Choose between round-robin dialogue for detailed analysis or summarized discussion for a summary of the discourse. These options provide researchers with a powerful toolkit to design novel persuasive systems, conduct empirical studies on interaction dynamics, and contribute to the theoretical understanding of AI-mediated influence. Now, let's put Apollo to the test. We'll demo two scenarios to showcase its flexibility for persuasive technology research. First, we'll explore ethical considerations. As you see, we're setting up a round-robin discussion. Notice that we are activating the harmfulness detection feature to ensure responsible AI dialogue, especially when dealing with sensitive topics. We'll prompt the agents with the unavoidable accident scenario, challenging them on decision protocols for autonomous vehicles. Before we run the simulation, let's review the specific prompt we're giving the AI agents. On submitting the prompt, Apollo begins the orchestration. Gemma, the first agent configured, is now generating its initial response to the scenario. After the first agent responds, the harmless label appears, confirming our safety classifier assessed the response and found no issues. This check happens for each agent's contribution in this configuration. The agents continue their deliberation turn by turn. You can follow the discourse turn by turn. This process continues until, as you'll see shortly, the agents begin to signal agreement. And there it is. The agents have reached a consensus. This concludes the discussion, allowing researchers to analyze the full dialogue chain, the persuasive strategies employed, and the final agreed-upon outcome. Now, let's explore Apollo's adaptability for domain-specific tasks. We'll activate Lawyer Mode to demonstrate how the system can leverage specialized knowledge and context. Notice how the system repurposes agents for the development of optimal legal strategies by modifying the system prompt. Next, we upload a sample court document, in this case, for a fictional wrongful termination claim filed by Jane Smith. Then, we need to instruct the agents. We'll use a prompt directing them to analyze this specific document and formulate a legal strategy for Jane. Now, running this full multi-agent discourse with document analysis can be quite computationally intensive and take some time. So for this presentation, instead of running it live, we'll load a previously recorded instance of this exact interaction using Apollo's Prior Conversations feature. Here, we see the recorded dialogue. Observe how the agents collaborate specifically on the legal task. Notice how they engage with each other and query the system. Those are instances of retrieval where relevant details are extracted directly from the uploaded court document to inform their arguments. This clearly demonstrates how Apollo enables goal-oriented, persuasive argumentation within a specialized context, providing a valuable way for researchers to study these complex dialogues. And as you can see in the log, just like a live run, the discussion proceeds until the agents collaboratively reach and signal their consensus on the strategy. Looking ahead, we see several key directions for enhancing Apollo's capabilities. First, we plan to expand domain-specific modes. While Lawyer Mode has been a compelling starting point, we envision pre-configured modes for areas like health coaching, educational support, and more. We also want to make it easier for users to create their domain-specific adaptations without needing extensive technical knowledge. Second, we aim to provide greater control over harmfulness detection. Currently, Apollo uses default toxicity thresholds, but future versions will allow manual calibration, giving researchers fine-grained control over specific toxicity categories and sensitivity levels. And finally, we want to enable agent-specific behavior customization. Right now, all agents operate from a shared system prompt. We're working toward allowing each agent to have its own unique persona, behavior profile, or instruction set, enabling richer and more realistic simulations of complex, multi-agent discourse. Thank you for your time and attention. If you have any questions, thoughts, or would like to collaborate, feel free to reach out to us. Our contact details are on the slide. You can also scan the QR code to explore the Apollo repository, where you'll find the full project. We hope you found this presentation insightful, and we look forward to staying connected.